Hi, I'm Alex,
I'm Matthew.
and we're both physicists at Stockholm University. So we thought we would have a little kind of uh, conversation, based on a question that was actually asked by a 6-year-old, Freddie. So we did like a small, more appropriately leveled video for that. But just such an interesting question, we really want to kind of explore it further. And that question is very simple. It is, what is outside the universe? And what happened in the Big Bang. Yeah, so there's a big open question there, which is the first thing with what do we mean when we say universe?
I mean, in some sense, the universe is, you know, I usually think of it as the universe is just defining everything that exists, the set of all things that exist.
Hmm.
So, I mean, when you talk about outside of that, then you're talking about things that don't exist anymore. That gets tricky.
It does get tricky, but it's but then it's a little bit tricky because people also use these words like multiverse or you know and sometimes you want to be a little bit more restrictive in your definitions because if you just call it everything that exists, that's true, but it's also becomes a little bit tautological in some ways.
Right. And especially once when you start talking about the beginning of the universe, the creation of the universe, I mean, your intuition that you're looking in on something which has a beginning means that you're sort of an observer outside of that, and everything gets a little bit tricky because if you're
Yeah,
like, well,
yeah.
am I within or without the universe? Do I exist or not?
Yes, when am I observing this universe?
Right. So what we often, when we're trying to get technical as physicists, what we typically think of is something called space-time, which is just the set of places and times that things can be or happen. So, I mean, usually when if you talk about an event, you can record, imagine you're reporting it at the paper. At 6:01 p.m. in front of City Hall, such and such happened, or so-and-so was seen. And so that list of position and time sort of defines the set of things that we think of as in space-time, just things that have a position and a time that they happen.
Yeah.
And
um
so we think of the universe as exactly the set of all positions and times that one could, reasonably write down for something to exist or happen.
yeah, and sometimes that's kind of the stage for which for people to act on.
Exactly.
Kind of mangling Shakespeare there. uh but I mean, the kind of the part that's really interesting, and when we get to this concept of the history of the universe evolving, is actually because the way Matthew described it, that sounds very static, right? And there's a very accurate explanation. But it turns out that if you look at different times throughout this set of all places will actually look different.
Or it has different properties.
It has different properties. Um, so when people are talking about how did the universe evolve or what happened or the Big Bang and things like that, you're actually talking about if you take, you know, the universe as a function of time, how this space-time is changing over that time. Um, for people who want to get a little bit technical, you can define a preferred reference frame in which to do this.
Right.
Um,
And
but
that's
which
where
I,
things
sorry.
that's where things in some sense get tricky. Is this is going back to Einstein. He's the one who started talking about, like, well, really space-time becomes a bit malleable when you
Yeah.
start talking about large things that have gravity. And so you have to actually start thinking about the way that space-time deforms, and it's a little bit intuition bending.
Yes. So it turns out that space-time isn't just, oh, it's a thing that something can happen in. Once you start placing objects in space-time, they will change space-time and then space-time will change them. And that thing is called gravity. So gravity is really just space-time reacting to the presence of energy. Um, but that's kind of this one, that's kind of the first counterintuitive thing about the expansion of the universe or the Big Bang. We're not really talking about the objects that much. We're talking about the space time.
Right? It's not the stuff in the universe expanding out. It's really the, in some sense, it's like the room that they're in is expanding.
Yeah. So
except the room doesn't have walls.
no, not necessarily. So one way of thinking about this is you imagine you have a ruler and you're trying to measure, say, the difference between the distance between myself and Matthew, which is about 1 Stockholm's worth at the moment. Maybe a half Stockholm's worth.
Half Stockholm.
You know. And then if you try to do it 6 billion years in the past, you would get a very different answer because we'd both be very, very non-existent. But in general, you would get a different answer. So your sense of rulers at different times and different places look differently.
This is a little tricky because it's not quite true when you're within a gravity well. But imagine Alex and I were floating in space, then absolutely.
Yeah. So one of the reasons why Matthew had to kind of interject this point is that when we talk about the expansive universe, we're talking about big picture. And on the very largest scales, the universe looks what's called isotropic. So everything looks kind of the same in every direction, and homogeneous, which means the stuff over here is more or less the same stuff that's over there in about the same quantities. And this is approximately true in the big picture, but it's manifestly not true in the small picture. The stuff around me is not the same as the stuff that's 1,000 light years in that direction. So these locally dense places, they're not experiencing the same changes to space-time that the average is. Because how we were talking about, this changing space-time is due to the presence of stuff. So locally, if there's a lot more stuff locally, that's not going to change in the same way that the average does.
Yeah. This idea of isotropy and scale is a little bit like looking at the sand on the beach. When you look at the sand on the beach, it just looks sandy and kind of flat. But if you're an ant at the beach, then you're, working through this huge maze of giant boulders and canyons. And so to us, it looks smooth and we can think about it as smooth. But if you really are an ant, then it's not.
Yeah.
True.
And in this case, we're the ants.
Yeah, exactly.
So it turns out that if you do this analysis and you look at the universe as a whole, it turns out the universe has to either expand or contract. It can only stay still, very, very small periods of time. It's just kind of the stuff that makes up the universe, the stuff in the universe, is going to force it to do either expand or contract. And this doesn't necessarily apply to an individual object. I'm not expanding. Our solar system isn't expanding. And in fact, it'll actually tend to get clumpier as the universe goes on. But the universe as a whole, it turns out, happens to be expanding.
Sort of like going back to the beach analogy, if you dump some water on the sand will spread out. But that doesn't mean the individual grains of sand are spreading out. It's just like the whole, if you're an ant, you might say, well, nothing's really changing. I'm just sitting here on my clump of sand. But, looking from above, you really can see everything kind of like moving apart as like water pushes the sand apart.
Exactly. So this is what, when we're talking about the expansive universe, we're really talking about this big picture scale things that you can run backwards and forwards in time because you can see how things are occurring. And in fact, that's exactly what we do when we look out into the universe. We run back in time. So this is due to the speed of light delay. So nothing goes infinitely fast.
Right. So one of the interesting things about this whole idea of universal expansion, because we can look out and actually observe, the galaxies, and there's like this complicated procedure that I won't get into called the galactic or the cosmological distance ladder that allows us to actually measure the distance away from other things in the universe. And the further away things are in the universe, we can see the faster they're moving away from us in every direction. So that means, in some sense, the universe is expanding in every direction. But that sort of, tempts us to ask the question, why, what happens if we think backwards in time? If everything's expanding out now, if we think backwards in time, shouldn't things get closer and closer together, more and more hot? And so this is sort of, the initial hypothesis that, some people called the Big Bang, actually criticizing the hypothesis. But the idea that, like, if you just extend this backwards in time, wouldn't you get some point where everything was really dense, closely packed together and hot? So, you know, as scientists, we're not just speculating about things. We want to actually be able to measure them or observe them. So one of the things we do is we look back in time with telescopes, which sounds a bit weird. Don't telescopes look at distant objects? Well, of course, the light from distant objects takes time to get here. So the further away an object is, the further back in time we're observing it in some sense.
Yeah. So just to give some kind of calibration scales, the distance between even say, here on the other side of the planet is so small that you wouldn't really be able to tell any speed of light delay. But from here to the moon, it's actually 1.3 seconds. So you're always seeing the moon about a second ago.
To the sun, it's about 8 minutes. So you're always seeing light from the sun about 8 minutes ago.
And if you go further away, like Pluto, it's about 8 hours. Right. And stars are typically, light years apart from each other.
The closest stars to Earth are about 4 light years away. So it takes light 4 years to get here from the closest stars.
Yeah. And you can just go further and further and further. And when you start looking at really distant objects, the times in the past are, billions of years.
So we can actually look backwards to a point when the universe was hot and dense and packed together. So if you think about it, like generally speaking, if you get gases hotter and hotter, eventually you what's called ionize them. This is like the glowing gas in the sun and neon signs and arc lamps and this sort of thing. And what's happening there is the electrons and the nuclei are being ripped apart. And so you have a bunch of electric charges running around and light bounces around and eventually is ejected from these things. So if you think about back in the early universe, there's actually a point where the universe was a hot glowing plasma and light couldn't escape it. Like the whole thing was just this glowing opaque mass, like a hot, dense, glowing gas cloud. And at some point,
very confusingly, this time is called recombination.
Exactly. So yes. So the recombination is when things cool down to the point where those electrons and protons slap back onto each other and the universe became transparent. And all that light that was banging around from that glowing gas just started streaming out. And we can actually look back in time and see that light at the moment that the universe became transparent. We can actually see that glowing cloud of the early universe 13.8 billion years ago. We call it the cosmic microwave background, microwave because it's about the frequency of radiation these days that you would see in a microwave oven.
Yeah. In fact, you could pick it up on old, those old CRT TVs, some of the fuzz from that is, from the cosmic microwave background.
Yeah, if you had a sensitive enough radio. So this is interesting. And one of, people initially actually thought when they observed it, people initially thought that it was some sort of interference in their devices. But the more they worked, they eventually discovered that actually, no, it's a real signal. It's coming, back in the 60s, I think they were originally discovering this.
By accident. It's a very funny
by accident. It's a really interesting story. But one of the craziest things, the reason that they thought that it was instrument error is because it's the same no matter where you look on the sky. It's exactly the same noise, whether you look that way, up, or down, which, I mean, is kind of strange because usually when you look at the sky, you expect different things from different parts of the sky. But no, it's actually exactly the same. And it's exactly the same frequency, which in physics terms means that it's exactly the same temperature in every direction. And this is really surprising. Well, go ahead.
It's just super odd. I mean, it's because of what we were just talking about with the speed of light delay.
Right.
Like we're talking about the furthest thing that you can see, which is 14 billion years ago in one direction, and then 14 billion years ago in the other direction.
There wasn't a universe 28 billion years ago. So How could they be exactly the same temperature? How did they know in some sense?
Yeah. If you imagine just going around your room, things that haven't been in contact very much, if I turn on my stove, it's going to be quite hot, and I come over to, a bed or something, they haven't had very much time to talk to each other. And hopefully not my house is on fire, so everything's the same temperature.
Right.
You would just naively expect things that aren't in contact to be different temperatures.
Right. If you turn off the stove, eventually it's going to be the same temperature as the other things in your house, but it does take some time.
Yeah.
And the two sides of the universe have not had time to come to the same temperature. So leads physicists to come forth with something called the inflation hypothesis. This is not something that's been proved, but it's pretty widely accepted because it fits the data quite well. And the idea is that at some point, not just this expansion that Alex was talking about was much, much faster. So fast, in fact, that it was faster than the speed of light. And those two sides of the universe that are 24 billion light years away from each other were actually in thermal contact as part of like the same very small, like peach-sized piece of universe. Very hot, very dense, very compact. And it expanded so fast that sort of like initial peach, and it, part of something potentially larger, but that initial peach basically expanded larger than, the distance that we can see, those 18 billion years, or 14 billion years, light years in either direction. The idea that it was so small that they were in thermal contact and were the same temperature is the only reasonable explanation that we've been able to come up with so far.
Yeah. But unfortunately, we don't have a smoking gun for this yet.
Right, exactly.
So it could be that there is another explanation that we are not aware of that is actually more correct.
Yeah.
I will slightly specify, due to the expansion of the universe, it's not actually, even if it was 14 billion years ago, the distance in today's terms is actually larger than 14 billion light years, because when the light's been traveling, the universe has been expanding.
And yes, exactly.
So if you were to try and go to that point now, it would be more like 40 billion light years away, just because space expands.
It's tricky. But that brings us to a sort of interesting point, which is the idea of the observable universe. And once again, as physicists, we're trying to do things that are grounded in observation or experiment. And so
most of us.
Sorry, what?
Most of us.
Most of us, right. Alex is more of a pure theoretical physicist. I'm sort of some weird hybrid.
Really, I was mostly talking about string theorists.
Okay, well. So, but the idea is that, there's the part of the universe, there is some pretty hard limits on the parts of the universe that we can actually observe. And that is, the parts that have sent light that we can actually see since the age of the universe. And so that's, what we call the observable universe. And outside of the observable universe, strictly speaking, we can't, make any conclusive statements. It's stuff that not only we don't know about, but something that we can't, in some cosmic sense, know with certainty about.
I will say that there are ways to guess about it. So
yeah, certainly.
A lot of cosmology is built off a kind of a principle of mediocrity, which is that we're just average. The universe, we're not living in a privileged place in the universe in an average sense. So even though inflation blows up just a small part of it, of the kind of the total universe, to be much larger than our observable universe, we kind of assume that the rest of that universe was more or less the same.
Right.
We don't have, while there are ways you could make the laws of physics look differently, there's no reason to assume that's the case. So probably those other patches, which were inflated very far away from us, probably they look relatively similar in general principles. But we don't have a measurement of this. This is just kind of, we probably shouldn't be some ultra special, super secret region, which is just the best one.
Some people, however, especially those who subscribe to something called the anthropic principle, kind of deviate from this assumption, though. And their idea is basically like, I don't know if I really want to get into it, but the idea of the anthropic principle is basically like, we can only observe universes that are conducive to human life. So, but yeah. Not everybody likes the anthropic principle. So the point being that, if you want to make conclusive, factually grounded statements, you can only make them about the observable universe. Yeah. Anything past that has to become a little bit speculative.
Yeah, just because it's something which by definition you can't observe. So
the other interesting, go ahead.
Yeah, and I was just saying that it's considered better to refrain from speculating too much on things you have no principal way of getting knowledge about.
Right.
No.
So one of the other interesting things about the idea of the observable universe is there are limits in space. There's also limits, in time. Certainly we can't observe before what we call the age of the universe, the sort of 13.8 billion years. And at least with optical telescopes, we can't actually observe anything older than the cosmic microwave background, because that's before that the universe was not transparent, and we don't get light from back then.
Yeah.
There are some.
It's actually very similar to looking at the sun. So the
Right.
sun is also this hot plasma. You're only seeing it from the outer surfaces where it's cooled down enough that light can actually escape. It turns out light takes about 50,000 years to get from the center of the sun to the outside, just because it just keeps bouncing around and getting absorbed and re-emitted, and it's a real mess in there.
Right. So in order to see before that, which in principle we could, we actually need new non-optical probes. We need something like, a better neutrino observatory, or looking at, certain ways of detecting primordial gravitational waves. And people are working on these, but we don't have anything yet.
Yeah. Neutrino's guys gotta be less lazy.
Exactly.
No, there are some limits. So this idea of inflation itself would be a problem. So the problem is by expanding everything, it essentially dilutes and homogenizes. So imagine, I give you an art history assignment on, I know, Jackson Pollock. And then instead of giving you a painting, what I do is I zoom in on some tiny patch of this, chaotic whole, and there's just a tiny bit of blue. And I blow that up so it's a full painting of just blue. And I don't tell you it's some minimalist painting. I tell you it's a Jackson Pollock. And I say, please speculate, what was the properties of this original painting before I blew this up? You can't really say much.
Yeah, it's really this, not just a don't know situation, but a can't know situation, which is, there's some fundamental limits to what we could ever know about the universe outside of that little sort of tiny speck from which the observable universe expanded.
Yeah. But that doesn't necessarily make us stop thinking about it.
Right, obviously you asked this question.
Yeah, I mean, there's a couple of points to it. One of them is, in principle, this question of outside, it's when we've bounded ourselves a little bit. We said, oh, well, you can't observe far further than this. We were just in this initial patch which got blown up, but there might have been much more of this patch. We can't really say observationally how large the whole of the universe is. It could be infinite. And there's no problem with an infinite universe expanding, though that's something which we would have a different conversation about what is infinity. Right. It turns out infinity can get infinitely bigger and still be infinity. It's weird. But, people will especially ask the question, not just what is outside. So in some sense, we've given some answers that outside of our observable universe, we would guess most likely there's more universe that looks more or less similar to us. But we can't know that. The other question that's kind of related in the other dimension is what happened before. So we can say it's hard to get information before inflation. It's not necessarily impossible. There are theoretically maybe some tricks you can play. Maybe inflation doesn't happen. Maybe there's another explanation. But at a certain point, when you run these equations back, the same equations that are explaining everything that's happened in the universe since, about a small fraction of a second, they stop working because you get to a point which is called a singularity. So a singularity in physics is basically just something that becomes infinite. So for example, we're running back this density. So the universe is getting denser and denser and denser and hotter and hotter and hotter. What happens when the distance between objects is zero? It stops making sense. And
usually once you get like singularities and infinities in your equations, it means the assumptions that you used when you're writing down your equations don't work anymore.
Yeah. And these can be a variety. It can be the fundamental physics is wrong. It could be some approximation you've made is wrong. It could be, it just tells you that there is some element that is lacking from your understanding.
Right.
So to explain this initial point, and this is a singularity that's in time, not in space. It's not like a black hole where there's a point which is confusing. It's everywhere. just at a kind of a single instance of time, if that even is allowed to be defined at that point. But it's when, space and time become infinitely dense, infinitely close together. And
But still potentially infinite extent. We don't know.
Until, yeah. So it's just telling us that the laws of physics that we're using to extrapolate back to that point are highly questionable. They probably just do not apply to that case. So any explanation for what happens before the Big Bang or, right at that initial singularity, they have to fundamentally deal with the fact that our understanding of space and time that we introduced right at the start as our definition, that's no longer working.
Right.
So it might be possible that space and time still make sense and that there's a laws of physics change that in some other way. You might have to redefine what you mean by space and time. Maybe one or both of them is some emergent property.
People talk about like theories of quantum gravity, which is essentially doing quantum mechanics on the fabric of space and time itself. Nobody's able to do it so far, but some people are trying.
Except in limited cases.
Well, yeah, exactly. And there's lots of people like to speculate on what happened sort of like at the very beginning. But, some people say basically like time ceases existing and space just folds in on itself. This was one of Stephen Hawking's theories. Some people like to say that it comes to a singularity, like Alex was saying. There's some idea like that it bounces, like it collapses and then bounces back out in a big bang. Or
personally, I find those ones are hard to get a bounce working properly.
Right, exactly. It's a lot of these have challenges, and one of the challenges, of course, is that it's almost impossible to measure, a prediction of any of them.
Yeah, one of the problems is our understanding works pretty well until you get to a totally extreme environment, super hot, super dense, and it's impossible with today's technology to really replicate that in the lab. So, and we don't have any direct observational points from it because of the problems of the cosmic microwave background and inflation. So you're really dealing with a case where you have no good observational data, lots of speculation, and also just from a purely theoretical point of view, it's really hard. The physics you have to deal with at that point has some properties that makes it really hard, even if you have an idea, to calculate anything using that idea. It usually starts becoming, the problem is, so gravity interacts with anything that has energy, which includes gravity. So these kind of self-interactions are really a nightmare to deal with. And
the chicken and egg problem on mathematically staggering scale.
Yeah. So at that point, we don't know what the correct description is. We don't know if something called time exists. So it's hard to say what happened before, because before is inherently a temporal question. It's hard to say what happened outside of, because maybe space doesn't exist. So you start just getting to a point where we really have run out of good knowledge.
Even the notion of cause and effect starts breaking down.
Yeah. I mean, some people like to rephrase it by saying, why does the universe exist? Not when did it come into being or something like that. But at a fundamental point, we're dodging that question because we don't understand it.
Yeah.
But maybe this has given some idea that, you have a really interesting question that can be asked by a 6-year-old. And while I guess we've shown you that throughout the last kind of 100 years of physics, we understand a tremendous amount more about the universe past a first fraction of a second. But if you get down to the really, really hardest point, it's something we still don't know.
Yep.
And this is also, on everything we've mentioned, there are a whole bunch of subtleties we could have gone into. The first version of this recording was twice as long.
Yeah.
And much more rambly. Very fun, though.
More rambly, if that's possible.
True. So, at the end of the day, it's just such a fascinating question because it really attacks our question of what do we mean when we say everything or universe? The intuition of space and time being treated as distinct things that interact and change, the fact that we have limits to our knowledge, both fundamental and practical, these are all super interesting things to think about. Yeah, so we thought this deserved a little bit more time than maybe could be properly expressed in a short answer video.
And of course, I'm assuming if you watch this video, you probably have lots of questions. Please feel free to drop them in the comment section, and we'll either address them there or maybe in another video. Or, in principle, we want this to kind of be an ongoing series. So if you have any questions just about physics in general, fundamental ideas or practical ones, ask away and we'll see what we can do.
Yeah, either in kind of short specific videos, which are kind of tailored to a certain level, or potentially more of these long rambles.
Conversational, please.
Sure.
All right. Thanks everybody for watching.